welcome here in my today's lecture on group theory. So in my today's lecture I will explain how to find out the total number of subgroup or subgroups of Z2 cross Z2 like integer group. Okay. So in my previous videos we learned subgroup of general linear group. Similarly you can find it for simple linear group. We learn it for quaternion group. For understanding their subgroups and how to find this subgroup easily, you can check it in my playlist. All videos are there. Okay. So now let's come here for my today's lecture, which is the group here Z2 cross Z2. Okay. So we want the total number of subgroups, how many subgroups are exist, and total number of subgroup in our Z2 cross Z2. Okay. So we know that Z2 is an integer group which contains 0 and 1 element. Okay. And this Z2 is also 0 and 1. Then take their Cartesian product 0 1 cross 0 1. Okay. So total number of element in a 0 1 cross 0 1 is a 0 0 0 1 1 0 and 1 1. Okay. So you can find this way. It is easier. And we know that the order of Z2 cross Z2, okay, it contains order 2, and this one is also 2. That means total number of order in our Z2 cross Z2 is a 4, okay. And we know that by Lagrange's theorem, we can say it here, our group can divide 1 to 4. That means our group is having possible order 1 to 4, okay. The divisor of a group is a possible order for our group. So now let's check out which one of the order is possible here, okay. So, and one more result here. So we know that result, identity and group G are always subgroup of group G, okay. So that means the identity element for Z2 cross Z2 and total whole group Z2 cross Z2, both are the two subgroups. That means we got the two subgroups here, okay. But let's find out by process, okay. So we know that for finding the subgroup of any group, we need number of subgroup of order D in group G, which is equal to total number of order DE in G, okay. That means total number of order in that G divided by pi of that element, okay. So if we want then one order of 1, okay, total number of subgroup whose order 1, okay. So subgroup of order 1 in a Zm cross Zn, that means Z2 cross Z2, which is equal to total number of order 1, okay. Total number of order 1, how many elements we have here of order 1? 0 0. Whose order 1? This is order 1, okay. And their LCM is 1, that means we have the only element whose order 1, okay. First order where who's having order 1, okay. So remaining element it is here, their order are 2 respectively, okay. So I have only one element whose order 1 divided by pi of 1. So in my previous video I explained how to find the Euler phi function, okay. So you can see that video. So 1 upon pi of 1. So pi of 1 remain 1. So 1 by 1, which is 1, okay. So total number of subgroup of order 1 in Zm cross Z2 cross Z2, which is 1, okay. And one order subgroup we know that, which is always identity, okay. So it is here 0 0, okay. So that first subgroup we found here H1 as a ideal generated by 0 0, okay. So it is a 0 0 here, okay. So I got the first subgroup H1, okay. Now let's move for the second one whose order 2, okay. So which are the possibility here? The element of Z2 cross Z2 who's having order 2, okay. So subgroup of order 2 in Z2 cross Z2. So number of element of order 2, which numbers are there whose element has having order 2? So respectively 0 1 1 0 and 1 1, okay. If we take their LCM we get the order 2, okay. So we have 3 elements, okay, whose order 2, okay. So 3 element whose order 2 and divided by pi of 2, okay. Number of element of order 2, that means number of element of order 2 is 3 divided by pi of 2, and pi of 2 is 1. It's Euler phi function, okay. So 3 divided by 1 is a 3, okay. So we have here total number of subgroup of order 2 in Zm cross Zn, which is a totally 3, okay. Like H2, H3 and H4 I consider 3 here, okay. So first it is here 0 1, ideal generated by 0 1. So you can take the nth power here and find out which element can generate by this ideal 0 1, okay. So 0 1 generated 0 0 and 0 1, okay. Identity always generate that element subgroup. Okay, now next we have 0 1 after 1 0 and 1 1, okay. So ideal generated by 1 0 and ideal generated by 1 1, okay. So 1 0 is a always generate identity element, okay. So I got the H2, H3 and H4. 3 are the subgroup whose order 2, okay. Already identity is the element whose subgroup is 2. So identity is element which is already subgroup here, okay. And H2, H3, H4, okay. These 3 subgroups, okay. Total I found 4 subgroup, okay. But now left over one more here whose order 4, okay. So you can take that group 4 with isomorphic to each group, or you can directly say by our standard result, every group is having identity and group G, both are the subgroup of group G, okay. Okay, so by using that one, you can say that last H5, which is a Z2 cross Z2, which is a subgroup of G, okay, which contain these elements. But let's find out by using the order of group, okay. So here by using order of group, order of G, which is 4, okay. So our divisor of a group G is 4, that means it is having possibility that group of order is 4, okay. So number of subgroup of order 4, okay. Number of subgroup of order 4, which is an cyclic or non-cyclic, we will check. Order of G is 4, that means fourth order group which is isomorphic to Z2 cross Z2. okay, which is a non-cyclic, and Z4 is a cyclic. Why it is non-cyclic? Because order of a G, which is a 4, okay, Z2 cross Z2 is having order 4, but the element which exists in a Z2 cross Z2 which do not have any element, okay, which do not have any element whose order 4, that's why it's non-cyclic. Okay, so we have to check whether our group which isomorphic to Z2 cross Z2 or Z4. Okay, now let's say check for if it is isomorphic to Z2 cross Z2, it gives the this one, okay, and Z4 Z2 cross Z2, our group Z2 cross Z2 is not isomorphic to Z4. It is isomorphic. We can see it directly because these two groups are same. That means they are 100% isomorphic. But Z4 is a cyclic. Z2 cross Z2 is non-cyclic, and our group is non-cyclic. So Z2 cross Z2 isomorphic to Z2 cross Z2, which is a non-cyclic group. Okay, and Z2 cross Z2 contain these elements 0, 0, 0, 1, 1, 0, 1, 1. Okay, that means we got the fifth number subgroup, which is our group G. Okay. So here total number of a subgroup which present here in a Z2 cross Z2, which is a total number of 5 subgroup. Okay. This one is easier example. So similar examples which asked in CSIR NET exam, GATE, SET, and multiple type of the competitive exam. Okay, which is an important topic in a group theory. I hope so you all have understood my today's lecture. It's quite easy for finding the subgroup from our group. So if you have any difficulty, you can ask me in comment section also. So thank you everyone. Thank you for my today's lecture.